Quantum field theory, QFT, is a theoretical framework in physics that combines the principles of quantum mechanics and special relativity to describe the behavior of particles and fields at the smallest scales of the universe. It is one of the most successful and fundamental theories in modern physics, providing a comprehensive description of how particles interact with each other through fields. To understand QFT, let's break it down step by step, along with some examples. Particles and fields. In classical physics, we describe particles, like electrons, photons, and quarks, as individual entities with definite positions and trajectories. However, in the quantum world, particles are often described as excitations of quantum fields. Quantum field. A quantum field is a mathematical construct that exists throughout space and time. It associates a value, a field value, with each point in spacetime. For example, the electromagnetic field represents the electromagnetic force and associates a value with each point in spacetime. Quantum mechanics. In quantum mechanics, particles are described by wave functions, which evolve in time according to the Schrödinger equation. In QFT, these wave functions are replaced by quantum fields, and the evolution is governed by quantum field equations, such as the Klein-Gordon equation for scalar fields or the Dirac equation for spinor fields. Quantization. To apply quantum mechanics to fields, we must quantize them. This means that instead of treating fields as continuous, we treat them as collections of discrete quantum particles, quanta. Each field has its corresponding particle associated with it. For example, the electromagnetic field corresponds to photons. The Higgs field corresponds to the Higgs boson. The electron field corresponds to electrons. Interactions. QFT allows us to describe how particles interact with each other through their associated fields. Interactions are mediated by the exchange of virtual particles. For example, electromagnetic interactions involve the exchange of virtual photons. Strong nuclear interactions involve the exchange of virtual gluons. Weak interactions involve the exchange of virtual W and Z bosons. Vacuum fluctuations. One of the most intriguing aspects of QFT is the concept of vacuum fluctuations. Even in the absence of particles, quantum fields are not completely at rest. They exhibit fluctuations or oscillations, leading to phenomena like the Casimir effect, where two parallel metal plates are pushed together by the pressure of these vacuum fluctuations. Examples of quantum field theory. Quantum electrodynamics, QED. QED is a QFT describing the electromagnetic force. It quantizes the electromagnetic field and describes how electrons and photons interact. An example of a QED process is Compton scattering, where a photon scatters off an electron. Quantum chromodynamics, QCD. QCD is the QFT describing the strong nuclear force that binds quarks together in protons, neutrons, and other hadrons. It involves the exchange of gluons, which are the force carriers of the strong force. An example of a QED process is Compton scattering, where a photon scatters off an electron. Quantum chromodynamics, QCD. QCD is the QFT describing the strong nuclear force that binds quarks together in protons, neutrons, and other hadrons. It involves the exchange of gluons, which are the force carriers of the strong force. Electroweak theory. This theory unifies the electromagnetic and weak nuclear forces into a single framework. It describes the exchange of W and Z bosons responsible for weak interactions, such as beta decay. Higgs mechanism. The Higgs field is a quantum field associated with the Higgs boson. Its interactions with other particles give them mass. This mechanism explains why some particles are massive while others are not. In summary, quantum field theory is a powerful framework in theoretical physics that describes the behavior of particles and fields at the quantum level. It has successfully explained a wide range of phenomena in particle physics and is a crucial tool for understanding the fundamental forces and particles that make up the universe.